Well, this will be a short class summary because in this class 11 we really didn't do anything new as far as theory goes, but just continued work problems with equations of motion with rectangular components. So remember our equations of motion for each the x, the y, and the z direction. We had the sum of the forces being equal to the mass times the acceleration in that direction. Just a little review. Remember that these kind of problems, all problems in kinetics, require you to draw a free body diagram. And so when you do that, you want to isolate the body from its surroundings and show and label all of the forces acting on that particle. That becomes the basis for writing your equations of motion. So your equations of motion should correspond to the forces on the free body diagram. One place to be especially careful is with your units. Don't confuse mass and weight. You have to use both of them usually in these problems. And so if you have a mass it's in SI units, make that mass in kilograms. Then if you need the weight, always multiply by g, 9.81 meters per second squared, to get the weight in newtons. In US problems, usually given the weight of a particle in pounds, divide that by 32.2 feet per second squared to get the units of slugs. And then as long as you're consistent with your units, then everything will work out okay. Now there is one type of problem that we didn't go over in the last class, but did in this one, and it involves a spring. So we've got a crate. It's connected to a spring. There's an applied force here. There may be friction on it as well. And what we want to know is if we start this crate from rest and we apply that force, what's the velocity after it's moved a certain distance? Now, what you want to recall here is that the force in a spring is going to be k times the deflection. So in this case, the deflection would be the distance s that we moved. So your spring force is going to be a function of s. So when you take the sum of the forces in the x direction, set it equal to the mass times acceleration, then your acceleration will also be a function of the displacement s. And so you have to use the equation that we worked in our kinematics. Whenever we had the acceleration as a function of s, we had to use this equation, AdS equals VdV, and so we can now integrate both sides to come up with the velocity after we've gone a specific distance. And next class, we're going to continue with equations of motion. But as we said, when we did the kinematics, we looked at three different coordinate systems. We looked at the rectangular coordinates, normal tangential coordinates, and then polar coordinates. And so we're doing the same thing here with the equations of motion. So next time we'll work some problems that involve normal and tangential components.